Thermochemistry students. So this is going to be Chapter 6, Thermochemistry. We're going to do all 3 learning objectives here in this one video, so it could get pretty long. I'll put in the times in the description so you can identify when things start. So this is going to be learning objective 1. The first question here, just to go over some basic concepts. The idea of energy, which is going to be kind of an important concept here, and specifically how it relates to work, because energy is really an abstract concept and doesn't really have any specific meaning unless we give it some kind of scientific terms. And so in science we say energy is the capacity to do work, and so then we have to define what work is. One way we can define work is force times distance. Another way we can define work, we'll see later on, is pressure times the change in volume, and this is going to be of gases, and this is applicable on chemistry because we have reactions that produce and consume gases which give us a change in volume. We have different kinds of energy: potential, kinetic, nuclear, thermal, radiant, all different kinds of energy. The ones that we're going to focus on are thermal and kinetic. Thermal is going to be the energy of atoms, the motion of atoms, and when they move around they have energy. And then the chemical is going to be what's stored into bonds. And so in chemical compounds, the bonds store energy, so it takes energy to break bonds, and you get energy back when you form bonds. And that'll be a really important concept in a future chapter. Some key words. We have the system, and that's what we're going to be focusing our attention on when we do problems. Unfortunately, we can't always measure the system directly, so what we do instead is measure the surroundings. If we can figure out what the surroundings are, then we can go back and figure out the system. So we're going to measure the surroundings, and that tells us information about the system. And that's going to be seen later on when we look at equations like this. Q is equal to negative Q. This is of Cis. This is of the surroundings. Or we could look at the change in energy is equal to the negative change in energy. And this is going to be Cis. This is going to be surroundings. And this idea of whatever the system does, the surroundings gets, and vice versa, is really important. In order to be able to study things, we have our system. We have 3 different kinds of system: open, closed, and isolated. Open allows for the transfer of energy and matter. This would be like an open beaker. Closed would be a transfer of only energy. So if you think about like putting a soda can into your refrigerator, that can is sealed, but it can still transfer its heat from the soda to the refrigerator so it cools down. And then isolated, this does not allow for a transfer of energy or matter. So you can think about putting a cooler, a styrofoam cooler, into your fridge and have something inside that cooler. It doesn't matter what happens to the fridge, that stuff in the cooler is going to stay cold for a period of time. It's very difficult to get a true isolated system, and so we use things like styrofoam and other insulators to get as close as we can to an isolated system. We have the different kinds of energy again, and the law of conservation of energy is going to be the first law of thermodynamics also, which says that energy cannot be created or destroyed. Heat and temperature, we spent a lot of time working on in class, and if you're still not sure about how that works, I do highly recommend that you do a YouTube search for heat versus temperature. Eureka. That's going to bring up that 5-minute video on heat versus temperature that I was going to show in class that we never actually had time for. So try that. We have more terms here. We have thermochemistry, which is what we're working on in this class. We're studying the transfers of chemical processes. We have endothermic and exothermic processes. Endothermic is when we have energy being absorbed by the system from the surroundings, and exothermic is giving off that energy. For example, water melting requires energy. In order to take water from a solid to a liquid, it takes energy. And the opposite would be true for water freezing. It gives off energy. We talked about this when we talked about the freezer and putting water in there. When we put water in a freezer, it doesn't get colder. We don't make it cold. What happens is we put it in an environment where the water is able to transfer its heat to the freezer, which is going to turn it into a solid. So that is giving off energy to the freezer in an exothermic process. All right, we have state functions. In chemistry, we love state functions. State functions say that it doesn't matter what path is taken in terms of a change, only the initial and the final. So we have the initial, we have the final. If we have those two values, we can figure out the change just by subtracting. Consider these changes below. Here the answers I already have written in, and we'll go through these different problems to figure out how I got those answers. The problem says at a constant pressure, so that's important, at a constant pressure, in which of the reactions is work done by the system on the surroundings, or the opposite, or when is there no work done at all? Now this is a good time to introduce this equation here. Work is equal to pressure times the change in volume, which means that work is also equal to this. Oh, I made a mistake here. This is the negative pressure times the change in volume, and we have change in number of moles RT, because P change in V equals nRT. So we can plug that in other place. So if we're looking at something like this, where we don't have a change in volume listed, we only have the chemical process, we can use this one instead. Now notice R is a constant, T is a constant, so work is only dependent on the change in the number of moles. If we end up with the negative for the change in number of moles, that's going to be system to the surrounding, because work is being done on the surrounding by the system. Anytime we have a negative, that gives the direction of from the system to the surroundings. Or the opposite would be true if it's positive. So if we look at a problem like this, we have 0 moles for our reactants and 1 mole for the products. Now, some of you may be a little bit confused as why we're using 0 here, but remember that in this kind of a problem here, where we're using an ideal gas law equation as the basis, things like liquids don't matter. It's only the gases. So we take 1 mole of gas minus 0. We end up then with a change in number of moles as a negative value. Work equals -1. So work is being done from the system on the surrounding. And you can think about it conceptually as well. So if we think about a system here, we have that mercury as a liquid, and now we have some kind of a cover on it, we'll say. So this is the surroundings that we're going to be able to measure, and it's attached to some kind of a device that will move things. Really struggling with this, guys. Apologize. Some kind of a piston there. All right. If this gas or this mercury liquid then changes to a gas, this is not to scale. It's going to expand, and so this is the surroundings that we're looking at, the movement of this piston against whatever it's pushing on, and so that's going to expand, and we end up having work being done from the system on the surroundings. So you can think about it conceptually as well. So the same thing here, we're going to put the change in number of moles equal to -1. In this case, we have a change in number of moles of, it looks like, 5. And in this one here, we have a change in number of moles of 0. 2 moles here, 2 moles there, so we end up with no work being done in this case. It does not change the volume. So it's important to be able to use this equation, substitute things in, identify constants, and figure out exactly what matters in terms of identifying whether or not work is being done by the system, on the system, or no work at all. All right, we get some math problems finally. We have a sample of nitrogen gas expanding from 1.6 5.4. We can figure out our energy, our work done in joules of the gas. This first one's pretty simple. Anytime we have against a vacuum, the pressure is equal to 0, so work is equal to negative pressure times the change in volume. So work is equal to 0 because of that pressure. So no work being done against a vacuum. You need to be pushing against something with a constant pressure. So we have a constant pressure of 0.8 atmospheres, so we can do work is equal to 0.8 times the change in volume is going to be 3.8. We end up with work equaling negative 3.04 liter atmospheres. Let me get the negative sign in there. And 101.3 joules is 1 liter atmosphere. Gets us an answer of negative 308 joules of energy. Do the same thing, but with 3.7 atmosphere, we end up with negative 1424.3 joules of energy for this one. All right. All right, we have another problem very similar, only now we have to incorporate work into the energy equation. We have a gas that does work at 325 joules, and then it absorbs 127 joules of heat. And so the first thing that we want to do is identify the signs on each of these. 325 is going to be a negative, because of the gas expanding onto the surroundings or into the surroundings, and then it absorbs 127, so that's going to be a positive 127. This is equal to work, and this is equal to, heat. All right, plug things into our energy equation. Energy is equal to work plus heat. Keep making G's. All right, so we can plug that in. Delta E is equal to work is negative 325 joules plus 127 joules. We end up with a value of negative 198 joules. Okay, now we get into a little bit more of a complicated one, similar to the problem that we did on October 17th, that there is a separate video for. So let's see what we can do here. All right, we have a reaction in which tin is reacted with an acid. It doesn't matter what acid it is, it's just going to be a net ionic reaction here, where if this was, say, like hydrochloric acid, it would be HCl, and then tin over here would be SNCl, and we would end up having whatever here cancel out. This is there, we'll do it that way, CN2. And so the chlorines will end up canceling out, so we end up with a net ionic reaction like this. So rid of this, most of it. All right, so looking at this problem, we need to first remember that we are dealing with work in terms of gases. So gases are the important part here. There's no gases on the reactant side, but there is a gas on the product side. It's going to be this hydrogen gas. So that's going to be the important thing. Start off with the reaction or the equation that we have. Delta energy is equal to Q plus W. And then we also have delta E is equal to negative 300 joules of energy plus W. And it's negative because it says this 300 joules of heat is released. So now we need to solve for work. And I'm going to do this using this one. Work is equal to negative pressure times volume, and show you this process. You could also do this process with work is equal to negative change in number of moles, RT. But this is the one I'm going to work with. So I can plug things in. Work is equal to negative 1 times 10.3 liters. That's going to get us 10.3 liter atmospheres. We have 101.3 joules per 1 liter atmosphere. That gets us negative 1040 joules. Plug this one into our work. So we end up with an answer of negative 1,340 joules. Now the question you probably have right now is how I got this thing here. So I'm plugging in 1 atmosphere. That comes from the problem, 1 atmosphere. Where do the 10.3 liters come from? I don't see liters anywhere in this problem. How did I get that? Well, I did 50 grams of tin. This is kind of the important part of the problem, the hard part. 50 grams of tin. And then 1 mole of tin is 118.7 grams of tin. 1 mole of tin. 1 mole of hydrogen gets us 0.421 moles of hydrogen. And we can plug that into this. 1 times volume is equal to 0.421 times R times 298. And volume comes out to be 10.3 liters. So this right here is the moles that we plug in to Pivnert. 0.421 moles of that hydrogen gas. And the reason why we put in only that 0.421 as the change in number of moles, because this is going to be change in volume, change in number of moles, is because that's the only gas we have. So we have, as a whole, according to this reaction, 0.421 moles of hydrogen. 0 moles here, 0 moles here, 0 moles here. We take products minus reactants, final minus initial, and we end up with that many moles of hydrogen. That's our change in number of moles. Plug it in, and we can go through the rest of the process. Again, we could have used this instead, so we could have done W is equal to negative 0.421 RT, and that would have gotten us our work, as long as you convert it into joules. and it would have come out to be the same way. Either way works. All right, let's go on to learning section 2. Some important key terms here, and the first one is enthalpy. This is a new term that we're going to be working with, and it is super important. And we spend the rest of the chapter using the term enthalpy. What we can say, though, is that enthalpy is equal to heat. We've already been using heat as a variable that we know and use to calculate with. Now we need to understand that it's also enthalpy, and it is exactly to enthalpy at constant pressure. If we're not at constant pressure, it's not the same. However, in this course, for this chapter, we will always be in constant pressure. Always be in constant pressure. We also have then some equations that we need to understand. We have enthalpy, which is H. I didn't put that here. Enthalpy is H. And so that's the variable that we're going to be using quite a bit now. So we have enthalpy is here is equal to energy plus the work, which we have. So here is work. We can also say then enthalpy is equal to the change in enthalpy is equal to the change of energy is equal to pressure times the change in volume. And again, we can plug in that same NERT in this equation where we take enthalpy is equal to energy plus NERT. And I'm going to bring this up right now, and we'll prove it in class that delta H is almost equal to delta E. Is that the right thing to do there? I don't know. It's not proportional or anything. It is almost equal. Is that what that is supposed to be? Should have looked that up. So it's almost equal. And they are so close that the difference between them is negligible. And so for the remainder of this chapter, except when we prove this statement, we use enthalpy and energy interchangeably, which means that heat and enthalpy are also used interchangeably. You may notice already this chapter that I have to watch my language in terms of how precise I am in using what term I want to use, either heat or energy. And the reason why that's difficult for me is because we often use them interchangeably. Heat is enthalpy, and enthalpy is heat, or excuse me, enthalpy is energy, mostly. All right. Enthalpy is a state function, which is good. And then this is the other part. Heat and enthalpy are equal under constant volume and constant pressure. Oh, no, that's right. I thought it was energy. Sorry. Yep. Heat and enthalpy, that's already here. Heat and enthalpy, it's the same thing, just written different ways. All right. Let's do a couple math problems related to this. Right here is a problem that many students get stuck on at the beginning, and it's frustrating for me as the teacher because it's stuff that we've already done. It's just going to be a conversion style problem. Not stoichiometry, but we're using this kind of stuff where we have the factor label dimensional analysis that we use in order to solve for moles and stoichiometry and things like that. So keep that in mind. All right, so it says that reading through this problem, the first step in industrial recovery of zinc. So we're looking for this stuff, or excuse me, zinc at the end. We take zinc sulfide and then we roast it and get zinc oxide. So we start with zinc sulfide and get our zinc oxide, and we end up with this reaction here. Calculate the heat evolved. These are key terms: heat evolved, released, liberated, given off. All of these things mean the exact same thing. It means that our answer is going to be negative. All right, so we have this here, 879 kilojoules is given off per mole of what's going on. And so we have to do some conversion work with this when we get further, but it's just a conversion factor. And this is per whatever mole of whatever substance we're working with. So this is per 2 moles of the zinc sulfide or per 3 moles of the oxygen, keeping in mind that whatever we're talking about in terms of it being a limiting reactant. All right, so we have 1 gram of it, because it says per gram, that's our starting amount. We can do then 1 mole of zinc sulfide is 97.46 grams of it. And then we have negative 879 kilojoules for every 2 moles of zinc sulfide. Think about this in terms of like our mole ratio step. So here's our 2 moles here, so 879 per 2 moles, and we end up with our value of 4.51 kilojoules. Same thing as here. Start with 1.26 times 10 to the 4th grams of nitrogen dioxide. So here's my starting stuff. 1.26 times 10 to the 4th grams of the nitrogen dioxide. Go through the process. 1 mole of it is 46.01 grams of it. And we have 2 moles of it. It's negative 114.6 kilojoules. I should cancel these units, huh? All right, so we end up with negative 15,691 kilojoules. All right, so there are those. Number 27 is very similar, but see students struggle with problems like this, where we're adding in a new component for this guy, which is going to be that delta E. You know what, though? Actually, now I'm looking at things. This is completely different than the other 2 problems. I should not have said that. We're looking at delta E here, and we're trying to solve for delta E. And this is actually that problem. I forgot this problem was on here. That this is a way that we can prove that delta E and delta H are almost the same, that the difference between them is negligible. So we start off here with our equation of delta E. So I should start off here with the problem. We have the reaction of water being split up into its 2 different pieces, and that energy required is 483.6 kilojoules. We have 2 moles of the water converted into 2 moles of the hydrogen and 1 mole of the oxygen, and it's going to be done against a pressure of 1 atmosphere, 125 degrees Celsius, and we want the delta E for this. Keeping in mind here that this is the equation that we are going to use, minus P delta V. Now that's just rearranging the equation that we had before of delta H is equal to delta E plus P delta V. That's the enthalpy equation. That's the definition of enthalpy. We just rearrange it to show E. So we have an enthalpy value. Now we want to calculate the energy value. Plug things in. Or actually, we're going to do some rearranging first. Delta N RT. We're subbing in the NERT instead of the PV. We end up with 483.6 minus the change in number of moles is going to be 1 times R, which is going to be 8.314. I'll come back to this again to talk about it in a second and remind you why we're using this one, times 4.8 times 10 to the 5th. Oops, what am I doing? 398 Kelvin, 125 degrees Celsius, 398. We're using that 8.314 because, again, we're dealing with energy. This is an energy here, so we want to make sure that we keep our units the same. And we can get that by taking 0.0821 liter atmospheres per mole Kelvin. 1 liter atmosphere is 101.3 joules. End up with 8.314 joules per mole Kelvin. And so that constant, again, is something that we will memorize and something we use very frequently. It's the other R constant. It's the other version of the R constant. All right, so we have all of this here, and I did make a mistake that I want to show you, and it has to do with this piece right here. Where we have the R constant, which is 8.314 joules per mole Kelvin, and this is 483.6 kilojoules. So one of these two things has to be changed. I'm just going to go ahead and change this one to 483,600 joules minus this, or minus that. 1 times 8.314 times 398 Kelvin gets us 480 thousand joules, which is equal to 480 kilojoules. And we can compare this to our original value of 483.6 kilojoules, and the difference between those two values is insignificant. 3 kilojoules, 3.6 kilojoules is a very, very small value of heat. So there's that. All right. For 28, just looking at my answer key to see if this is one that I could skip over, and it doesn't look like it. Consider, it looks like it's different enough that we should work on it. All right, consider this reaction. If we have 3 moles of hydrogen reacts with 3 moles of chlorine to form hydrochloric acid, calculate the work in joules against a pressure of 1 atmosphere, and then what is the delta E. So we have two different processes here. We're solving for work, and we're going to solve for energy. And we have a pressure of 1 atmosphere. All right, so the work is going to be negative pressure times the change in volume. So work is negative 1 times 0 for that guy there. And the reason why the change in volume is 0 is because we have 2 moles of reactants and 2 moles of products. I said that backwards. We have 2 moles of products and 2 moles of reactants. It still comes out to be the same thing. So the change in the number of moles is equal to 0. So if we did work is equal to change in number of moles RT. If we have 0 here, work is equal to 0. So delta E over here is equal to Q plus W, And we don't have a W, so delta E is just equal to delta H, again because Q is equal to delta H at a constant pressure, which it is a constant pressure of 1 atmosphere. Oftentimes we use a subscript C to denote that something is constant. Now the only piece in here then that we need to account for is that we have 3 moles of this, 3 moles of this, and now we're producing 6 moles of this. And so we're going to have to multiply this value also by 3. And that's something that we look at here in this chapter in a different place, where the values of this is related to the stoichiometric function of the coefficients. So if this is 1, 1, and 2, we have our enthalpy value for what's going on here. If this is 2, 2, 4, we would multiply this by 2 as well to get that value. So in this case, since we did 3, 3, 6, we're going to multiply this by 3 as well and get our value for delta E, which is going to be negative 533.8 kilojoules. And that is our answer for that guy. All right. Consider the data here. So this is getting into the idea of specific heat. And specific heat is equal to the amount of energy required to raise the temperature of 1 gram of a substance 1 degree Celsius. So if we had, for example, 1 gram of water, it is the amount of energy to raise the temperature of that 1 gram of water 1 degree Celsius. And incidentally, the value for this is 4.184 joules per gram degree Celsius. So if you had 2 grams of water, it would be double this, because it'd be joules per 2 grams degree Celsius. So that's the idea of specific heat. In general, the lower the specific heat, the better the conductor it is. It is going to be able to transfer its heat better than something with a high specific heat. We'll use S to denote specific heat. So if we look at this problem here, we have copper with a low specific heat. We have aluminum with a higher specific heat. Therefore, the copper with a lower specific heat is going to be able to transfer its heat to aluminum more easily. So the overall temperature here is going to be, oh, sorry, that's down here. So I just got lost, guys. Hold on. Oh, so this is a different kind of problem. You guys are going to have to forgive me here. So all of this is going to apply to the next problem. This one is much simpler. We have 2 metals placed in contact. Aluminum transfer heat to the copper, or will the copper transfer heat to aluminum? And the copper is going to transfer heat to the aluminum because the copper is at a hotter temperature. The thing with a hotter temperature always transfers its heat to the thing to a cooler temperature. What we're going to use this information for next is to figure out which one of these 2 things is going to transfer the heat better. So where is the final temperature going to be? All right, so let's go on and look at that thing. But here, this is very simple. Well, with the hotter temperature, it's going to transfer to the lower temperature. All right, so now going on to this guy here, look at this one. Again, let's look at that specific heat and bring that up again. Joules per gram degree Celsius. The thing with a lower specific heat is going to be able to transfer its energy more easily to the thing that has a higher specific heat. So more energy is going to be transferred here. So the final temperature here, when we put these two metals in contact with each other, is going to be less than 50 degrees. Both have the same mass in this case, and the problem before, we saw that it was only the one, the copper had a larger mass, and that was kind of unimportant in terms of the problem. What matters here is the temperature. If they both have the same mass and they have different specific heats, we can look at the specific heat and determine in which way the heat will be transferred more quickly. So the one that has a lower specific heat is going to transfer its heat more easily than what the aluminum is going to be able to do, and so it ends up with a temperature lower than 50 degrees. This is a really kind of difficult concept to get, and we'll work on it in class a little bit more, but without having questions, I'm not sure exactly how else to explain that. The one with the lower has a better chance, or is better at transferring its heat than the one with a higher specific heat. And so if we reverse these two things, if this was 60 degrees and this was 40 degrees, then the temperature would be hotter than 50 degrees because aluminum wouldn't be able to transfer its heat as well to the copper like copper can the other direction. All right, now we get into some application questions related to enthalpy and heat. We use this equation, Q, which is heat, is equal to mass times the specific heat times the change in temperature. This is often referred to as QMSAT. Q is equal to M times specific heat times change in temperature. And that means that the mass is important, not the mole. So this really throws a lot of students for a loop, where in thermochemistry, the mass of the object is important, not necessarily the moles. So we have that in this problem. So we have this problem, what is the specific heat of silver if the heat capacity is 85.7 joules per degree Celsius? Now the difference between heat capacity and specific heat is that heat capacity is for a specific mass, in this case 362.6 grams, where specific heat is per gram. So in order to do this problem, all we have to say is 85.7 joules per degree Celsius divided by 362 grams, and that will get us 0.237 joules per gram degree Celsius. This one isn't going to be necessary to work with in this case because we're not given a change in temperature. We're just given heat capacity. But this is the basis of all of the problems we're going to be working on from here on out. So for example, 33, 6,220 grams times 0.385 joules per gram degree Celsius times a change in temperature of 303.8 degrees Celsius. I want to talk a couple things about this problem right now. The first one is change in units here. We have 6,220 grams. Notice I changed it from kilograms to grams. That's because our specific heat is going to be in joules per gram. Those units have to match. The second part here is this 0.385. That came from table 6.2 in the textbook. I do not know the page number of that off the top of my head, but table 6.2 has specific heats of several metals. The other one here is the change in temperature, 303.8 degrees Celsius. Notice I use degrees Celsius here, and not Kelvin. That's because we're looking at the change in temperature. And the change in temperature from, we'll say, 0 degrees Celsius to 1 degree Celsius is equal to 1. And if we did the same thing with Kelvin, that would be 273 Kelvin to 274 Kelvin is 1 Kelvin. So when we are looking at the change in temperature, the change in temperature of degrees Celsius is going to be the same as the change in temperature of Kelvin. So either way, Celsius or Kelvin, we are fine here. So we end up doing all of the work here. Q is equal to 727.5 kilojoules. Notice my answer is in kilojoules. If you left it as 727,500 joules, that is perfectly fine. It's a little bit of a large, unwieldy number, so I like to change it into the kilojoules. Just like, it doesn't make sense to run 160,000 centimeters for a mile. You're going to run 1,600 meters. That same sort of thing. So put it in a number that makes more sense. All right. Calculate the amount of heat liberated in kilojoules from 366 grams of mercury when it cools down from this to that. Before we do that here, guys, let's go back to this one real quick. This is heat absorbed, and so the value is positive in the end. This one we have heat being liberated, so our answer is going to be negative in the end. And our answer comes out to be negative 3.31 kilojoules of energy. And again, we use this. And there's our answer. All right, 35 is probably my favorite question on this entire assignment because it gets to use this thing right here that we talked about. The Q of the system is equal to the Q of the surroundings. Now that's not 100% applicable here because we don't have a system and surroundings. What we have is two different systems that are coming into contact with each other. And if we read through this problem, we see those two different systems. We have a piece of gold and we have a piece of iron. And we're going to take these two metals and we're going to sandwich them together and see what the final temperature of the two is at the end. The important things here, we have a mass, we have a temperature of the gold, we have a mass and the temperature of the iron. What is the final temperature of the metal? And then this is important, assume that no heat is lost to the surroundings because of this assumption here. And so we are going to go through here and say, instead of Q of cyst equals Q of the surroundings, we're going to say the gold is equal to the heat of the iron. Now, it doesn't matter which one of these two things you label as negative and which one you label as positive. It will, the signs will work themselves out at the end. Now, the other part of this, though, is that we don't know the heat. We can't calculate the heat because we don't have a final temperature. So we're trying to figure out. So if we did Q equal to ms delta T for, say, the gold, we couldn't figure this out because we don't have a change in temperature. We don't know what that final temperature is. What we can say, though, is that since Q is equal to ms delta T of gold, we can then say the mass times the specific heat times the change in temperature for the gold is equal to the negative mass times the specific heat times the change in temperature of the iron. Plug things in, 10 grams times the specific heat, 0.129, times the change or the temperature, which is going to be T final minus 18 equals the mass 20, specific heat 0.444 times final minus D5.6. Now I'm going to skip through the algebra here. We end up with the final algebraic step of 10.2 final temperature equals 517, and that gets us 50.7 degrees Celsius. So there's our answer there. All right, number 36. This is a very similar problem to 35. Only instead of using two different metals, we're taking that metal and we're putting it into water. So we can still use that same equation or that same idea that the heat of the water is equal to whatever heat of the aluminum given off. And notice that the aluminum is the hot temperature here, water is the cold temperature, so the aluminum is giving energy from it to the water, so we can use a negative sign here for the aluminum. If we put the negative sign with the water instead, it would still work out. We can do our work here, mass, specific heat change and temperature equals the same thing here. And in this case, we're looking for the mass of the water. And we have a change in temperature. Mass here. Remember, the change in temperature always comes from final minus initial. The final is going to be this, 24.9. We start with an initial temperature of the water of 23.4. So it's 23.4 to 24.9. That's our change in temperature of the water. The initial temperature of the aluminum is 81.7, but it doesn't ever tell us what the final temperature of the aluminum is. We make the assumption that all of the energy has been transferred from the aluminum to the water. If that's the case, if all the heat has been transferred from the aluminum to the water, then the final temperature of the aluminum is also 24.9. So we can take 24.9 minus 81.7, we get negative 56.8. Do the algebra, we end up with a mass of, oh, I do not have the answer for this one done. I apologize. Whatever answer that is. I got approximately 100 grams of water. My calculator says 98.6. So say it's about 100 grams of water. All right. That was learning objective 2. So let's see if we can finish up fairly quickly with learning objective 3 and talk about the enthalpy of formation. Now, by definition, the enthalpy of formation is the amount of energy that is given off or received when we form 1 mole of a compound from its elements in their most stable form. For example, water, which is H2O, is made up of hydrogen plus oxygen. Both of these are gases. That makes water, which is going to be our liquid. This process releases negative 285.8 kilojoules per mole. There. Now notice that we have this caveat of being per 1 mole. We're producing 2 moles here, and so we need to change this then, so we have ones for the coefficient, and then we'll have to put a 1/2 there. So 1 to 1/2 to 1 gets us our heat of formation of that. All right, we're going to apply this then to the problems. Anything in their most stable form at 25 degrees Celsius is going to equal 0. Something like sodium as a solid is going to be 0. Neon as a gas, 0. Methane is a chemical compound, so not 0. Sulfur, this is its chemical formula as its most stable form. Mercury is good, it's a liquid, 0. Mercury is a gas, not 0, because it is not its most stable form as a liquid. Bromine gas, also not 0, because bromine in its most stable form is going to be a liquid. Water is not 0, it's a chemical compound. Iodine is a solid, 0, we're good there. We have 2 different allotropes. That means 2 different possible chemical formulas of an element like this. We have oxygen diatomic, and then the ozone version of oxygen. We have 0 and 142.2, which is more stable. Of course, it's going to be oxygen. That's how it occurs in its most stable form. All right, so here is where those state functions come in really handy. Enthalpy is also a state function, and so if we want to solve for the heat of combustion for processes like this, actually let's bring up again some key words here. We have heat of reaction, we have heat of formation, we have heat of reaction, combustion, we have heat of vaporization, that's evaporating. We have all of these different kinds of enthalpy values. We call them heat of things. And they all mean the same thing. It's just what they're being applied to. So this is heat of combustion because this is a combustion reaction. All right, so we go to the appendix and we look up the different heat of formations for these, because the heat of reaction is going to be the difference between the products and the reactants' heat of combustions. So we take our enthalpy value for A and look up water. Water is negative 285.8 kilojoules per mole. And we subtract our products from that, which is going to be 0 because this is 0 and this is 0. End up with negative 571.6 kilojoules. Not confuse you guys. And do the same thing with B. Products minus reactants. This is a little bit more involved here. 4 moles of carbon dioxide, 393.5, plus that of water, which is going to be that negative 285.8, minus the reactants. This is on one of those tables in there in the back. It is there. 2 times 226.6 plus, oh, I guess we can show this 5 times 0. So we have 5 times 0 for oxygen. And that gets us 2,600. And I'm assuming that's a negative number. I don't have it listed on there. All right, so that's how you do these kind of problems. Products minus reactants, super easy. Same thing for 54, same concept. A equals negative 1411, and then B equals negative 1124, and that's kilojoules and kilojoules. For number 57, it says, well, it's just more of the same. It is, yeah, I do want to add to that one. Negative 3294 kilojoules. For 56, we're solving for a different piece. And so far we've been looking for that heat of reaction, but number 56, we're given the heat of reaction. It is 436.4. So that's going to set equal to our two hydrogens, and so that is 2 times X is what we'll set it to, because again 2 moles of those. And then we'll subtract that from our reactant side, which is going to be 0. So X is equal to 218.2 kilojoules. All right. Now we get into the fun stuff. These are our Hess's law problems. And so there's two different ways to calculate heat of reactions. One is through this called the direct method, and the other one is the indirect method. And that has to do with Hess's law. For the sulfur problem, we are going to figure out how to rearrange these two guys so that it comes out to equal. Put it down here. Sulfur rhombic to sulfur monoclinic. And as we practice in class, guys, we want to get everything to the correct side of the chemical reaction, and we want all the coefficients to match, and everything else will cancel. So if we flip this around, we end up with SO2 goes to sulfur monoclinic plus our oxygen. Notice now we have the sulfur on the right side. And then everything else that we don't want cancels, because if we have the same thing on the reactant side, on the product side, it goes away. Adding these things together, the sulfur dioxide cancels, the oxygen cancels, we're left with the rhombic and the monoclinic. The key part here is that when we do things to the reactions, we also have to do things to the enthalpies. If I flip this, I have to flip this. End up with positive 296. So the overall answer here is going to be 0.030 kilojoules per mole. Let's see. Here is the graphite problem. I'm just going to use that as my line I'm adding up. And this is how we end up doing this one. We take this times 2, so this gets multiplied by 2. This one gets multiplied by 3, so this becomes 3 halves, and this becomes 3 waters. This one becomes actually in half, so this goes here. This becomes 3.5, or another way to say that's 3 halves. This becomes 2, and this becomes 3, and it gets flipped. So I end up with 2 carbon dioxide plus 3 waters, makes C2H6 plus 3.5 oxygen. And then we can see this stuff canceling. Oop, I should do this first though. Multiply this by 3, so that becomes times 3. We've flipped this one, so this becomes a positive value, and it divides by 2 because we divided everything by 2 here. So we end up canceling everything we need to cancel. Let's see, where am I canceling first? The carbon dioxide cancels here and here. The oxygen cancels. We have 1, 2 here, and we have, let's see here, 3 halves there, which is 1.5. That's 3 halves to, or 3.5 there. 1.5 plus 3.5, or 2. So 2 plus 1.5 is 3.5, and we end up canceling that out there. I'm going to get rid of this here, guys, because that's messing me up. This one is no longer important to us. And our waters, 3 waters cancel here. We're left with our graphite, our hydrogen, and our ethane. All right, so there's that one. This one down here is going to be a little bit easier. We're going to flip this first one. So we end up with CO2 plus 2H2O. CH3OH plus 3 halves oxygen. I just remembered I didn't give you an answer here. It's negative 84.6. All right, so there's that. This one doesn't change at all. This one goes to doubled. All right, and go through and make the changes that I did. This one is positive now. And this one is times 2. And then we can cancel things. Get rid of this guy here. All right. Now we can cancel stuff. Carbon dioxide goes away. Ooh. Carbon dioxide goes away. The oxygens partly go away. So we have 2 oxygens here and 1.5 oxygens here. So 2 and 1.5 leaves us with 1/2 of oxygen. We have the hydrogen there, we have the graphite there, we have that there, and the water's less than it cancels. Water cancels. All right, so we're left with 0.5, 1/2 oxygen. And there we are. Oh, I did that backwards, didn't I? Apologize. So 1.5 oxygens there and 2 oxygens here, so we're left with 1/2 oxygen there. So our oxygens match there. One more problem here for our enthalpy stuff, our Hess's law, and this one here, all we have to do is flip this guy around, and this becomes positive. So this is positive. An answer of negative 847.6. All right, last stuff here, guys. Enthalpy of solution and that process there. Recall that energy can be stored in bonds, and so when we break bonds, that takes energy. When we form bonds, we get that energy back. And whenever we dissolve a solid salt into a solution, we can think about that process in terms of it having its bonds broken and then new bonds being made. Although the attractive forces between the ions in the water isn't a true bond, it's still an attractive force that then releases energy. So we have the enthalpy of solution, which is that process, the energy that's either given off or absorbed when that process occurs. The lattice energy is that breaking of those bonds. It's taking that energy to separate those things, those ions, into their solid parts and into their gaseous ions. This is by definition, guys, that doesn't actually happen in an aqueous solution. We don't see gaseous ions, but by definition and how we calculate these things, that is the value that we're going to be using, gaseous ions. And then heat of hydration is then the opposite, is the enthalpy process of then putting those ions with those water molecules so they end up dissolving into the solution. And then heat of dilution, so this is going to be the solid stuff. We take like salt and dissolve it in water, where dilution is taking like aqueous hydrochloric acid and then dumping it into more water. So we have that dilution process, and then there's going to be an enthalpy process associated with that as well. All right, lattice energy. We just talked about that. Now, let me bring it up again. You're always requiring energy to break those bonds, that's the lattice energy, and then you're always getting energy back when those ions are hydrated, which is kind of a formation of a bond, an attractive force anyway. And so if those two statements were not true, the solid ionic compound would not dissolve. We have to break bonds, we have to form bonds. If one of those energies is the opposite, it wouldn't happen. And that's why it's always the case. It always takes energy here, and it always gives off energy here. So takes energy positive, gives off energy negative. Last problem. This gets into some stuff that we aren't going to study until next chapter, but it's a good introduction. We're looking at which species has a larger hydration energy. So when it dissolves in that solution, once we break them into their ions, which one is going to release more energy, that magnesium ion or sodium ion? And there's two different reasons here for the same answer, which is magnesium. Magnesium is the right answer here. And right now, probably the only one that is going to make a lot of sense to us is the fact that this has a larger positive charge. Larger positive charge, more attraction to the aqueous, or to the water molecules to become hydrated. Larger attraction, it's going to release more energy. And so we have that one there. Also, the other part is the size of the ion. The magnesium is going to be a smaller ion than sodium. If it's smaller, it's going to be able to attract to those water molecules better. There won't be as much shielding of a larger ion of those electrons in the nucleus away from the other water molecules. So that's something that we'll talk about more in chapters 7 and 8. So right now, probably the only one that you need to worry about is that charge, not the size. All right, guys, that finally gets us through learning objective 3. Hope this was helpful.